All right, so this is the third lecture of number theory. The purpose of today's lecture is to just talk about coding. So I really want you to leave Williams knowing basic coding. There's an enormous amount you can do with just for loops, while statements, if, whatnots. There are some other videos I will post online from slightly different variants of this lecture I've given over the years. I also have more extensive templates, whatnot. I'm going to use Mathematica not because I think it is the best program, but because it's what I'm very familiar with, and it has a lot of functions that are predefined, especially functions that are useful for number theory. So I want to start off with the cookie problem. So we talked about the cookie problem last time. I think I have, nope. Okay. Okay. So cookie problem. We have C cookies, and they are identical. And we have P people distinct. How many ways can we divide the C cookies among the P people? Now, as soon as I write this, I'm implicitly making some assumptions. What assumptions am I making?
Possibly people are distinct, cookies are not distinct.
Well, okay, I've actually made that explicit. That's an implicit assumption. No, you're not allowed to speak today. And you're not allowed to speak. Anybody who is in probability is not allowed to speak. So what do you think I'm assuming about the division process? Yeah.
That you won't be splitting cookies up?
I'm not going to split cookies up. I'm not going to give somebody 3/4 of a cookie and someone else 1/4 of a cookie. What else?
It's instantaneous?
It's instant.
It doesn't really matter, like when you give cookies to people.
Sure. Yes.
That everyone can eat cookies and can use as many cookies as they want.
Sure. And this is actually a really good one. That there is no cap on the number of cookies. You might say basic fairness. It is just wrong if this person gets 8 out of the 10 cookies. Or maybe I want everybody to get at least 1 cookie. If I give 1 cookie to the 3 people here who have seen probability with me in the past to eat for themselves, and I keep the other 9 cookies for myself, have I divided the 10 cookies among the class? Yes. Is that what you're assuming when I say how many ways can we divide the C cookies among P people? You're assuming that I'm giving out all the cookies. Now you could of course do the related problem where you divide or distribute at most C cookies up to C cookies. You really want to spend the time to clearly state what you're doing. So what I want to do now is I want to go through a couple of ways of attacking this problem. So the first one is the function C cookies 5 people. The names are supposed to be extremely descriptive, so when you look at this function, you know what it's doing. Probably dividing C cookies among 5 people. What's in the brackets here is the variable. It's the input to the program, and you put an underscore in Mathematica. So num_c is going to be an input. The colon equals means I'm now defining this as a function. Module is how Mathematica likes to write function. The curly braces here means I have no local variables. Anything I use in this function can be seen by the rest of the notebook. This is often dangerous, but I'm very careless sometimes when I program in something like this. If you want to be very careful as to what sees what, you can use local variables, and then you can use the same name in different places. You always want to be careful, have I overridden a name? You really want to have some comments. This is such a straightforward program here. I'm not going to have that many comments. I will have more comments later when we get to the number theory. So num_c is the number of cookies to divide among 5 people. And it goes as follows. I'm doing a quintuple sum. Sum. AI is the number of cookies person I gets. Each one can range from 0 to num_c because you can get at most num_c cookies. And I look and see, add up how many cookies I've given. If that is exactly equal to num_c, then this is a fair division. And I count this as a success. So if this equals num_c, it's a 1. Otherwise, it's a 0. And as I go through all the possibilities, that will tell me the number of legal divisions, the legal distributions. Okay? You could write this with one sum command and just have 5 things over here. If I go to another Mathematica window, If you do a question mark and then sum, it will give you information about the command. And then if you click on the double sign over here, it will expand out and open yet another window, and you can see, here's how it does multiple sums, I, j, but then the summation goes ji. Okay, so I do this sum last, this sum second to last, and so on and so on. It's always good to have a second window open to just test a bunch of things. So Shift-Enter compiles something in Mathematica. Timing is just going to tell me how long it takes to run something. So I'm going to time it to divide up 20 cookies. Or better yet, let's do 10 cookies. I'm impatient. So it takes about 0.17 seconds to do 10 cookies. How long do you think it would take to do 20 cookies, given that it takes about 0.2 seconds? So how would you estimate how the runtime grows with this algorithm? I want to double the number of cookies I'm dividing. Well, look at the sums. The sum goes from 0 to num_c. So if I double the number of cookies, what am I going to increase the runtime by? What would you guess?
I feel like they're trying to get us to say that it would double the runtime, but that doesn't.
2 to the 5.
2 to the 5. Each sum is going to double. And I have 5 sums. So it should be a factor of 32. So I would expect this to be around, so it's taking 0.2 seconds, 30 seconds, maybe around 6 seconds or so. No, I didn't double it. So it should be a little bit less than 6 seconds. So it should have been done by now. Okay, 4.4. Now sometimes when it's so small like this, it's tough to tell. So now if I have 4, if I go up to 40, how long should it go from about 4.5 seconds? This should now be a little bit over 2 minutes. So I'll let it run right now while we chat. This should give you ballpark 2 minutes. It's nice to get a rough sense of how long something is going to be. Is this algorithm practical? We talked about the dream world last time, where every subatomic particle in the universe was a supercomputer devoted exclusively to our use, running since the dawn of time. Most of the time, we're not going to have that as an option. So you really want to think about better ways of doing things. So the next one is the cookies 5 people slightly faster. And what you notice is there's only 4 sums. And the reason is, if I divide the cookies among the first 4 people, how many cookies should the 5th person get? Whatever's left over. So I can get rid of an entire variable. So if I'm going up to 40 cookies, how much should this save me? How much faster should this be? I'm sorry?
4 times faster? Or a factor of 4, right?
Well, I'm now dividing 40 cookies. So what kind of factor should I save if I get rid of one summation loop? So this, yes, 40 times faster. Because all of it is going, each loop is going from 0 to 40. So technically I think I'm saving 41, but 40 is close enough. By getting rid of one summation, this should be 40 times faster than this one. This one still hasn't even finished. I'm still pontificating, and it's still computing away. Okay? This one should run in about 1/40th of the time. So, if you have about 2.5 minutes, every 40 seconds in the old one should be 1 second here. We're talking on the order of maybe 5-6 seconds at worst. Right? That's much better. Okay, so this took 122.7 seconds, around 2 minutes. If we run this, this should be much faster. This should be on the order of 4 seconds at most, and there you go, about 2 seconds. And if you multiply 40 seconds by 0.6, that's about 24 seconds. So 40, 40, 20. So ballpark, these runtimes are comparable. It's about what you should be getting. So a slight change in the code saved us a factor of 40. And as things get higher and higher and higher, it's going to get more and more useful. Now the problem is I want to sniff out the answer. I want to sniff out the pattern. When I look at 40, hopefully that's enough data. This is taking on the order of 2 minutes. Can we wait 2 minutes? Depends on the situation. You're in the middle of a battle, and turns out, small misunderstanding, your own guys are firing on your position. And you want to radio to headquarters, excuse me, please aim your weapons at the bad guys, not at us. Well, how does headquarters know that this is not a message sent by the bad guys trying to trick them? This is where you would use cryptography and codes. You don't want to have to spend so much time encrypting your message and having them decrypt it. You want some very fast ways to transmit information. Efficiency is often exceptionally important. Can we do better? So this one is even better. And the code, it's almost the same length. It's 4 sums, but the problem here is as soon as the first 2 people, let's say we're trying to divide 10 cookies. Once the first 2 people get 11 cookies, does it matter how many cookies the third person gets? If I'm trying to divide 10 cookies and the first 2 people have already received 11 cookies, no, it can't work. So what I'm going to do is A4 goes from 0 to the number of cookies minus the number of cookies the first 3 people get. A3 goes from 0 to the number of cookies the first 2 get. A2 goes from 0 to the number of cookies minus the number that the first person gets. And this way, A1 plus A2 plus A3 plus A4 will be at most the number of cookies. I no longer need my if statement. If the sum was less than or equal to num_c, it's 1, otherwise it's 0. I don't need this because I've now forced the sum to be at most the number of cookies. So it was taking the faster way about 2.6 seconds to do 40 cookies. If I try doing this now, it's taking 0.03 seconds. If I want to go up to 200 cookies, 200 cookies I was able to do in an extremely reasonable amount of time. This was, I think, on the order of 4 or 5 seconds. Okay, 6 seconds. Okay. So you can see with spending just a small amount of time of thinking about things, you can have enormous savings. Theoretically, does it really matter which one of these we use? No. All right. A huge part of this class is sniffing out patterns. If you know the answer, it's often a lot easier to prove it, especially if you're trying to do a proof by induction. If I tell you, prove the sum of the cubes up to n is n squared n plus 1 squared over 4, the proof essentially writes itself. Write the sum of the first n plus 1 cubes, use the inductive hypothesis for the sum of the first n cubes, put that in, do some algebra, show that they're equal. The proof writes itself. If I don't tell you what it's supposed to equal, however, it's a lot harder. So the idea is, can we sniff out the answer? And now again, this will give us enough data points that we're fine, but we may be in a problem where it's not so easy, and we really do need to worry about these efficiencies. I want to show you, a really nice trick that involves some number theory stuff that we've been talking about in class already. And it's just a nice way to convert from this to coding. Are there any CS people in this room right now? Okay, you will know better ways of doing this than what I'm about to show you, but what I'm about to show you is a nice idea, and it relates to the theory we're doing, and I can't do an entire class on coding, I'll go crazy. I need to do some math content. One of the difficulties is we want the number of people and the number of cookies to be variable. But when I'm writing things, it helps to know I want to do 5 sums or 4 sums. It helps to know that ahead of time. What if I don't know ahead of time how many sums I'm going to need because I don't know how many people they're going to be? I need to do a variable number of sums. Here is a really nice way to do a variable number of sums, assuming each sum has the same number of things. Now, if you notice here, this one actually has a significant amount of coding. So I'm going to talk about the theory first. All right, so here's the cookie problem. So let's say now C equals 10, P equals 5. Okay, so each person can get from 0 to 10 cookies. Okay? What I'm going to do is I'm going to work base 11. When you work base 11, what are the digits base 11? So what would be the digits base 11? Yes?
0 to 9.
Yeah, 0, 1, dot, 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 9, and in honor of Roman numerals, we'll do an X. So what I can do now is I can count in base 11. And the first digit will be how many cookies the first person gets. The second digit, how many cookies the second gets, third and fourth. So if I give you the number 3412 in base 11, this is going to be 3 times 11 cubed plus 4 times 11 squared plus 1 times 11 plus 2. I don't care what number that is, that's just what it would be. Okay, it looks better, I guess, writing it like this. And what this means is first gets 2, second gets 1, third gets 4, fourth gets 3. Does this work? Is this a valid way to divide 10 cookies among 5 people? What would the fifth get? Yes. We get none. So this would actually work. So the number 3412 in base 11 would correspond to the fifth person getting screwed and getting no cookies, fourth getting 3, third getting 4, second getting 1, first getting 2. So this is a great way now to just count. So I would now count from 0 to XXXX. And then what I would do is add up how many cookies I've distributed among the 4 people, and if that's less than or equal to 10, I have a legal way to assign cookies to the fifth person. Okay? So this is a nice way to handle a variable number for loops. All right, so let's see the code. So now I start off by explaining what the inputs are. So parentheses star star parentheses means this is comments in through here. So num_c is the number of cookies, num_p is the number of people, count is 0, and I'm going to count the number of successes. The key idea is I'm counting from 0 to num_c plus 1, so that's the base I'm working in. If it's 10 cookies, I'm working base 11, to the number of p minus 1. And the reason is I can do this summation trick and get rid of one sum. If I want to have 4 digits, you have to remember the first is 11 to the 0, 11 to the 1, 11 to the 2, 11 to the 3. And then I subtract 1 so that my largest would be XXXX. So this is very similar to what the Babylonians were doing. They did base 60. For this problem, base 11 is better. What class should this remind you of, where I'm changing the base from base 10 to something else? That's a better base for the problem. You should have seen this in a class. Yes?
Comp sci with binary.
So when it's comp sci and binary, and your computers love binary, on, off, yes, no, true, false. But there's a math class that has this idea of changing base. Linear algebra. The whole point of linear algebra is to choose a base that's convenient for the problem. If I give you an ellipse where the axes align with the coordinate axes, it's really easy to do. If I give you an ellipse that is not aligned with the coordinate axes, it's much harder. And so what I can do is, let's see. If I give you an ellipse like this, and if you have a really good imagination, that's an ellipse, it's not aligned to the coordinate axes. But what I do is I draw some new axes like this. And with those as my axes, I can now write down the equation of the ellipse in that basis. And then I do a rotation to get to the basis that I want, the xy basis. That's the whole point of linear algebra. Find the basis that's most convenient for the problem you're doing. Here, the most convenient base is num cookies plus 1. So now what I'm going to do is, the same thing as if the sum is at most num cookies, then I can give the remaining cookies to the new person. So Mathematica has this wonderful function called IntroDigits. It converts n to a list of digits in another base. Now you've got to be a little bit careful. What is 15 base 11? So what would the number 15 look like in base 11? 14. But I want to divide things among 4 people. I need to write this 14 not as 1, 4, but as 0, 0, 1, 4. So if you use IntroDigits, if you use a third input, that third input says pad your number so it has a bunch of zeros in the beginning so that you have a fixed number of digits. It's so wonderful that it has a function like this predefined. This is one of the reasons I think Mathematica is a good program to use for a class like this. It has a lot of functions that will just make our life easy. So now what I do is I just count from 0 to numc plus 1 to number of people minus 1 in steps of size 1. Take my number n and convert it to base num cookies plus 1. Pad it with zeros. Sum the digits. So sum of xi, so in Mathematica, x is now going to be a list. Double brackets is what I need to choose an element from the list. I'm choosing the first element from the list. And I'm summing from 1 to num p minus 1. That's the number of elements I have in my list. If that sum is at most num c, I increase the count by 1, and then I print the count. So now, let's run this with 20 cookies. And see how, so it takes about 1 second. That's not bad. So if I want to run this with 40 cookies, it took 1.2 seconds. About how long should this take? Will this fill up the rest of the class? About how long should it take to do with 40 cookies? I've doubled. Do you have, I was going to say you don't have that much time.
18 seconds.
Yeah, about 18 seconds. So I was actually surprised it went as fast as 18. So the question is, does this one go through things as linearly as the others? The other thing which somebody noticed from the last class is when we're counting, once the first digit is an x, is the number of cookies, is there any reason to continue assigning cookies and counting from that point onward? No. We could have actually shrunken how high we're counting here with a little bit more work. All right, now what I want to end with is, let's look at what's going on with 5 people. So I'm using my fast cookie counter. It counts for 5 people. It can do the first 20 cookies without too much trouble. 5, 15, 35, 70. I mentioned the online encyclopedia of integer sequences. In Mathematica, I can print out a web link like this, and I can actually just click on this, make this in my notebook. And so I've already posted, I pasted this into the online encyclopedia of integer sequences. And it says, hey, these are the binomial coefficients, binomial n choose 4. And here's my number. Now, if you notice, my 5 is not the first term of the sequence. There seems to be a little shift going on. But the fact that it's telling us that it's a binomial coefficient is huge. If we're trying to figure out what the answer is, this is a really good hint. It's telling us that the answer when you have C cookies and 5 people is going to be something choose 4, where that something is going to be a little bit of a tweak on the number of cookies. And we can figure out exactly what that tweak is. If you think about what's going on, and when the camera's not rolling, I will tell you maybe why I have a cookie monster and how I got him. I want to divide 10 cookies among 5 people. Imagine we have 14 cookies, and Cookie Monster, the cookies are in a line. Cookie Monster comes and gobbles up 4 cookies. Okay? So let's see, we should be able to have him actually do this. It's a great Cookie Monster. All right, he gobbles up some cookies. How many cookies are left if he gobbles up 4 from 14? 10. Everything up to the first gobbled cookie goes to person 1. Everything between first and second gobbled cookie goes to 2, between second and third to 3, between third and fourth to 4, and after fourth goes to 5. There is a one-to-one correspondence with the ways Cookie Monster can eat 4 cookies from 14 as there are to divide 10 cookies among 5 people. So the answer is just 14 choose 4, or better, C plus P minus 1 choose P minus 1. Having this here is an enormous help. The other thing you can do is you can try to do special cases. Instead of doing 5 people, what should you do first? What would you do?
Some small number.
Yeah, how many people should you start with?
I guess 1.
1, right? This is the same thing. Oh, we didn't do the queen problem in this class, right? Do simpler cases first. Just because somebody gives you a hard problem doesn't mean you can't do an easier problem first to build intuition. Try to see what's going on. Try to divide C cookies among 1 person. All right, so C equals C, P equals 1. How many solutions are there? How many ways? I'm sorry? One. Person 1 gets all the cookies. Kind of boring. C equals C, P equals 2. Number of ways is C plus 1. Once I give a number of cookies to the first person, the number of cookies for the second person is now determined, is C plus 1. And then we can continue. If I have 3 people, once I assign a number of cookies to the first person, then I've now reduced it to an earlier problem. Right? So now if I have C equals C, P equals 3, number of ways, so I'm going to have a sum. K goes from 0 to C, right? That's the number of cookies the first person gets. If the first person gets K cookies, how many cookies are left for the other 2 people to distribute? C minus K. How many ways are there to divide C minus K among 2 people? C minus K plus 1. C minus K plus 1. And now we just have to figure out what that sum is. Well, the C plus 1 is constant, that comes out, and now we just have a sum of K. We showed on the first day of class how to handle that. You can actually now use this and get a formula, and you might notice that it's a binomial formula. You might not. But you can then begin to see, now we'll have a formula for here, and then we can see, oh, induction. And you can see if I have a polynomial, the next one's going to be a polynomial as well. I'll know what the degree is. You can get a lot by doing small cases. So again, the purpose of this class is not to race through and see how much content can we do. I really want to go slowly through the material and emphasize how to think about these things. There are not that many chances in life to take a class leisurely. How many of you have taken Calc 3 at Williams? I got to be careful because I'm teaching it next fall. In some sense, it's my least favorite class to teach. I love you guys all next fall. Next spring, because there's so much material you have to get through. I feel that if I die and they're trying to decide if I get into heaven or hell, and I cannot say I taught Stokes' theorem, I'm going to be denied admittance. You can't go through Calc 3 and not see Stokes' theorem, or at least Green's theorem. That's a lot of material to cover. I also feel you need to see Taylor series. I also feel you need to see Lagrange multiply. And the list just goes on and on and on. The solution is either then you have to start cutting other things. We don't really need to do too much motion on curves. Or you have to go at a really fast pace. It's a 12-week semester. There are other schools that have 14 weeks or more. We're lucky here. We are not in a situation like that. So the online encyclopedia has a lot of wonderful information about this series. We can do small cases. We can build intuition. So this is a wonderful problem. It uses the math we're discussing. It uses bases like the Babylonians. It gives us an introduction to coding. All right, I want to move on to another problem now. So the problem is the following. You have the digits 1 through 9. Use each once. Form 3 fractions. Form of a over bc, which is a divided by 10b plus c. Okay? Want the sum to equal 1. Is this possible? So for example, I could do 3 over 48 plus 9 over 21 plus 7 over 56. That's not going to equal 1. Is there a way to choose my numbers? So let's try to think about how difficult of a problem this is. How many ways are there to assign numbers? Yes?
It's less than 9 factorial, but like you can start with 9 factorial.
Sure, we can start with 9 factorial, which is about 362,000. Now, we have on the order of 10, 20 people in the class, so each of you will get about 36,000 or maybe 18,000 things to go through tonight. Not surprisingly, on Friday, attendance falls to 0. Right? We're not going to do this by hand. How about a computer? Can a computer crunch through 362,000 objects? Yeah, these aren't that big. A computer would have no trouble going through the 9 factorial possibilities. We could do a little bit of a savings. When I have my 3 fractions, does it matter the order in which I write them? No. So if I wanted to, what kind of factor savings could I have if I do something about the order of the fractions? What could I save? A factor of 6. How many times do I have to run this program? Once. Right? Once I get the answer, do I need to run it again? Am I going to be changing the input? No. This is very different than the cookie problem, where I would say, okay, let's have more cookies. I'm not going to have more cookies. How much time do I want to spend making my code efficient? Do I want to spend 5 minutes making the code more efficient when the code runs in less than a minute? It's not a good use of time. If this was for a cell phone, if this was for data transmission, if this was for streaming video, and I worried about bandwidth, absolutely would worry about efficiency. But if it's something I'm only doing once, is there a need for me to program well? No. And so I would much rather write an inefficient, crappy code because I only need to run it once. Okay? So I'm not going to worry about this. So when I was at a Top Math Institute several years ago, somebody had mentioned this problem. And some of my colleagues are beginning to prove results about where the 5 and maybe the 1 and the 9 must be. And they're having this chain of lemmas. And it takes me less time to write the code in Mathematica and to just brute force it than for them to prove their lemmas. Now, they have a much better theoretical understanding of what's going on. I didn't really care or need that for this. All right, so let's look at some things in Mathematica. So here is a way to put things in a list. 1 through 9, and I can just add it one at a time. Another way is I could assign the list to be empty, and then j goes from 1 to 9. J++ means increment j in steps of size 1. List is going to be append to list j. I'm going to just make a new list, and then I'm going to print out the list. Now, perm list, again, I want good names, is the permutations of the list. So over here, let's type permutations. And so it says permutations list generates a list of all possible permutations. Permutations list n gives all permutations containing at most n elements. And permutation list n in curly braces, all permutations containing exactly n elements. I want all permutations, so I would just do permutations list. So that's 9 factorial. 9 factorial, if you want the exact number, is about 362,880. If I don't put a semicolon after a command and I do shift enter executes things in Mathematica, oh, I didn't recompile this. So my list is now 9 elements. It's going to try to print out all 362,000 elements. And then eventually it says, I don't want to do this. Here's the first couple. I'm going to skip a little bit over 362,000, and then I'm going to print out the last few. And I'm going to tell it, no, I really want to see a little bit more. So Mathematica thinks a little bit more. It sends me a few more to the screen, but it's still hiding most of them, saying, you really don't want to see all of these, do you? And eventually I'll put in the semicolon and go, yeah, you're right, I don't. But it did not take it that long to create a list and have all of this. My feeling is it is probably not storing in memory the list of all these things. It's probably storing a quick way to assess the possibilities. Okay? And so now what I can do is I'm going to go to my main window, and here's the program that I wrote from class before. So list is initially empty. If you notice there's no function, why is there no function? Last time I was defining things, I had cookies, C cookies, P people, and I had 2 variables with underscores, and I had module. Why am I not doing that now? Why is I have no variables. I'm running it once and only once. There's no need. So list is empty. Then I add the numbers 1 through 9 to the list. Perm list is going to be the list of all permutations. So then n goes from 1 to 9 factorial in steps of size 1. X is perm list. I'm just going to pull one of my permutations out. And then what I'm going to do is I'm going to form the fraction. Double brackets means I take the first element of x and divide by 10 times the second plus the third. In Mathematica, like a lot of systems, you don't need to put a multiplication if you're multiplying two quantities. I'm putting these things in parentheses. How many of you have ever met a dear Aunt Sally or Sarah? Please excuse my dear Aunt Sally or Sarah. The order of operations, parentheses, exponentials, multiply, divide, addition, subtraction. So unless you tell things otherwise, these are the orders in which systems like Mathematica process commands. I do not believe I need these parentheses. I feel more comfortable with the parentheses. And so now I just have my three fractions. I add them together, and if this, you need a double equal sign equals 1, I'll print out x. And you can see how long it takes to run. All right, I'm not even going to bother putting the timing. 1 Mississippi 2. And this is why I'm not really concerned about making the code efficient. The runtime is so negligible, just coded by brute force. And if you look at the answers, you see that there are 6 answers. Is it surprising that there are 6 answers? No. We have 6 things to try. I'm sorry, once we have an answer that works, we can move things around 3 factorial to 6 ways. As a fun problem, generalize this. So how might you generalize this? Yes?
Do it for any base outside.
Yes, so try to do it for another base. So I really want you to be thinking about this. Generalize. Whenever you see something in mathematics, what else could I do? Is this a special case of a more general phenomenon or a process? What's really going on? Often if you can see how things vary, you can have a much deeper understanding of what goes on. And when we were trying to do the cookie problem, I don't want to just do it for 5 people. I want to see how is it depending on p. It turns out there's a lot of great math related to this. So we could generalize to another base. Do we want all the fractions to be a 1-digit numerator over 2-digit denominator? Do we want everything to be used once? Do we want to maybe allow 2 digits over 2 digits? You have choices. Why would we choose it to be 1/2? Why would we choose it to be 1 and not 1/2? Could we go to this code and see maybe is there any way to get it to equal 1/2? There is. Are you surprised that there are 6 ways to have it equal 1/2? Is there a way to have it equal 1/4? So here's my conjecture. Wow, there's a lot of ways to have it do 1/4. Given any rational number, there's always a way to do it. What do you think of this conjecture? False. Why is this false? I've got 3 data points.
There's some really, really small.
I have some really, really small. What is the smallest my fraction could be? 1/98, right? And I have to then add 2 other things to it. So as an interesting exercise, how many rational numbers can you attain? How does that vary as you vary the base? The numbers like having it equal 1, these are particularly interesting because these are integers. We could try having it equal 2. Is there a way to have it equal 2? No. What about 3? Is there any way it could equal 3? No. Why not? Yeah, all the numbers I'm adding are less than 1. I don't even have to run the code for 3 or higher. Is 2 possible? Well, maybe. I've got 3 numbers. But if I have 3 numbers adding to 2, at least one of the numbers has to be how big? 2/3. Then you would need 2 numbers to be at least, is this possible? And if you have one number that's really large, how large could the next one be? So you might even be able to prove theoretically that you can't get up to 2, without even running the code. Because if I have a number that's too large, I need to have 2 numbers that are pretty large. So again, there's lots of things you can do like this. Okay? And we can start exploring a bunch of things later on. Are there any problems people would like to see coded? If not, I'll do the next problem, which was brought up by somebody in the first class today. So they're calling this the subset problem. So consider a set of n distinct elements. Take any subset A of n. Take a subset of A of n, call it B of A of n. How many ways can you do this? Okay? So unfortunately, I typed the wrong command. I typed permutations rather than subsets, so it didn't work out in the first class. We actually theoretically predicted what the answer should be. So let's do it without doing the answer, without knowing the answer. Okay? So everybody understands the problem. We have 1 ... n. We choose a subset A of n. Then we choose a subset of that, B of A of n. And we want how many B of A of n are there. And note, you could have 2 different A's that give rise to the same B. You'd count that B twice. Okay?
Is this problem different from just taking a subset of the original?
So the question, so if it's just taking a subset of the original, how many ways would there be?
2 to the n.
So the way it's different is I could have intermediate steps.
So different intermediate steps would make it a different set B.
No, it's the same set B at the end, but I would count it multiple
Distinguishing
times.
between it.
I'm distinguishing between them. So now what matters is not just what you are, but how you got there.
Okay, sorry, the B of A of n confused me.
Right.
It sounds like just
Right. So I'll take an example. Let's say the Patriots were leading 34-0 with 3 minutes to play, and Atlanta slowly is scoring points, and we win in regulation, 34-28. Is that the same game as the Patriots being down by 25 and scoring, in 4 consecutive possessions, going to overtime and winning? It's the same score at the end of the game, but the process of how you got there matters. So for a lot of things in life, how you get there is important. So here, it matters. You could even go another layer. You choose an A, then you choose a B, and then you choose a C. You could do this at most n times and say, what can you say about the answer? So here's the code. So the function is going to be called subset function. The input is going to be n. It's going to be the number of elements. I'm not using capital N because Mathematica likes to reserve capital N to take numerical values of things. So the colon equal means it's going to be a function. So I use module. I have no local variables, 2 curly braces. And when I'm writing, I like to type the closing braces immediately as I follow the beginning ones. Okay? So what I'll do is I'll just delete some of this at first. And so I will put the closing brace in immediately. I set my count to be 0. I set my list to be empty. And now, bless you, what I'm going to do is I'm going to add j goes from 1 to n in steps of size 1, and I'm going to just make a list of the first n numbers. Okay. Next thing I'm going to do is perm list, and that's a really bad name. I'll call it subset list. Will be the subsets of the list. Now again, whenever you're using something, you should always do some tests. And so I was doing perm lists. That was the wrong thing. If I do subsets with the 2 here, it's going to give me all subsets of the list with at most 2 elements. So if I do now 1, 2, 3, 4, how many subsets should there be of the set 1, 2, 3, 4? So how many subsets? I see you said nodding. How many subsets should I have? Any thoughts? So for each element, I have 2 choices. I include it in my subset or I don't. So it should be 2 times 2 times 2 times 2. There should be 16 subsets. Because for a given subset A, you either choose an element or you don't. And if you look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, but this is doing all subsets of size at most 2. And then what I can do over here is I can do length of subsets list 4. And the length is 16. So subsets 4 will give me all subsets of size at most 4. So now I come over here, and subset list will just be the list of all subsets with at most n elements. And now what I'm going to do is, if m goes from 1 to the length of, I'm now calling this subset list. And now I'm going to use the fact that if I choose a subset of size 5, the number of subsets that has would be 2 to the 5th. So once I know what my A is, I know how many B's this A generates. So all I need to do is I keep my running count, and I increase count by 2 to the length of the set A. Okay? So let's run the program for 1. And when I run it with 1, I get an answer of 3. That's one data point. Can you figure out what this function is from one data point?
You actually have 2 data points, because you can also look at 0, because you know 0 is 1.
So 0 should be 1. So we could do that. So now let's see what actually happens if we put in 0. Will Mathematica be happy? Oh, okay, Mathematica was actually happy. Wasn't quite sure that would work. So what I could do now is, let's do the following. For num equals 0, num less than or equal to 10, num plus plus. And what I'm going to do is I'm going to print what my number is. I'm going to then put a space, and then I'm going to print how many subsets of the subsets it has. And this would be a nice little table.
You have to return.
I'm sorry?
In our subset function, you haven't returned anything, so that's why.
Ah, I didn't return anything, thank you. I did have the print count though, but okay. So we'll return, thank you. So we'll return count now, and we'll pass that out. Oh, and we're printing the count here, so I'll suppress that. All right, so now, and if I wanted to, I could have printed out headings for these columns. Class is about to end. I'm not going to spend too much time making things look nice. 0, 1, 2, 3, 4, 5, 1, 3, 9, 27, 81, 243, 729. Anybody want to guess the pattern? Yeah.
3 to the n?
Yeah, it looks like it's 3 to the n. So this is the advantage of doing some coding like this, is the pattern now is screaming at us. So how can we figure out what the answer is? Well, let's quickly go to the following. Set of size k has 2 to the k subsets, right? How many A's have k elements? It's n choose k. Right? I have n objects. I choose k of them. I want A to have... So the answer, so how many B of n, or B of A of n? It's going to be a sum, k equals 0 to n. It's going to be n choose k. And then it's going to be 2 to the k. Now, the most important thing you can learn how to do in mathematics is how to do nothing. There are 2 ways to do nothing. You can add 0, and you can multiply by 1. And one of my professors, Peter Jones at Yale, said the log of 1 is 0, so there's actually only one way to do nothing in mathematics. How should I multiply by 1 here? Any thoughts?
You multiply by 1 to the n minus k.
Multiply
Each term
by 1 to the n minus k. And then I have the binomial theorem. You know, we have the sum k equals 0 to n. I'll write it as n c k, just to save some space. 2 to the k, 1 to the n minus k. How many of you have seen the binomial theorem? So this is now the binomial theorem. The answer is now just 2 plus 1 to the n. This is the binomial theorem, which is just 3 to the n. And so there's the proof. Okay, so this is a good place to stop. I'll post other coding things online. I strongly urge you to do some basic coding. If you have questions, if you want more, just come to me, talk to me. Happy to chat about this. All right, if you could hit stop. All right.